Alrighty, so let's start talking about gain bandwidth again. We fired up LT Spice, and I had a schematic, and I was just looking for parts, and I chose LT 1630, and you can open up the test circuit there. Okay, and I ran it, and you can see that the oh, that's not good. There we go. So some things, right? It's a fourth order circuit, four capacitors that can't be reduced, right? And so a low pass filter would be 90 degrees for every order. So that's 4 times 90, 45, right? 45, 450, right? But notice the phase is actually going more than that. And the simulation is just hiding the messiness from you, which is okay. Okay. So, yes, it's a low pass filter, but there's some, oddities going on. Now, yeah, out by 10 megahertz, okay, um, that's 10. Let's just say 10 megahertz. Okay. The gain is minus 110. All right. So don't get excited about digital design just because it's there. Okay, so let's say we have 1 volt in, right? The gain was minus 110 divided by 20. So 1 volt in gives us milli, what, 3.1 microvolts. So even though we're having some issues here, right? It's not ideal. It's starting not to matter because the attenuation is so great. All right. But this is um, now, yeah, your oscilloscopes, I think, go to 70 megahertz in the lab, and the ADLM is about the same. So it'd be hard to measure past this anyway. And remember, the part is only guaranteed to one, no, 30 megahertz. So that's 20, 30. So right around here, yeah, the part is not really supposed to be used or working. Now, I'm not going to extract the ideal voltage, the ideal response here, but this should be a straight line. And where does it stop working? Well, when it stops being a straight line. I'm going to show you other examples, right? But yeah, so let's look at the gain bandwidth of this. So I'm just going to delete everything. And it's a single supply circuit, which takes a bit of explaining. So I'm going to change it back into a dual supply. Okay. They updated LT Spice on me after like I don't know. Been using it since 2013. So okay, so now let's run it. And I'm gonna take it out to 1 hertz, so hopefully we can see. Oop, number of points. Oop, my bad. So this is the real gain bandwidth plot of a device, a high-speed device. You can see though that here's the gain, 90 dB, and when they say high precision, that means at DC there's a high gain, right? So the open loop gain is 31,000. Now there's like lower frequency parts where it's 800,000, right? So that's that trade-off I was talking about. But really, let's double check. Is the game? They said it was a 30 megahertz part. So here's 0 dB. What frequency are we getting? Hmm. I don't like that. I mean, did we all see that it said 30 megahertz? Hmm. So the gain bandwidth is actually 7.6 megahertz. All right. Now, yeah, um, this phase, that's 124. Okay. But it's real. All right. And an IC designer, the person who designs the op amp, has to try to get that. If I were to lower the frequency, I could get this phase hump to come down. All right. But we're pushing the limits. All right. So, I'm a little concerned that what I read is not what it is. So let's go look at the data sheet. So right click here, go to Analog's website for data sheet. Okay, let's go. Let's see, about us. Oh, come on. It used to come right up to the part. Like it would load the part. But Analog Devices bought a lot of folks. Oh, here we go. Okay. LT 1630 product. Okay. You know, you can get free samples. Just saying. Oh, maybe I gotta click on data sheet. All right. Gain bandwidth, 30, slew rate, low supply, all these great things. Okay. Let's just click on the data sheet. I recently having a hard time with Adobe products. Um, I'm sorry. When I get upset at a software company, usually I'm the one to suffer. So I'm suffering right now. Okay. The slew rate is just the maximum slope of the output. Okay. I don't have my magic markers. So, okay, here's all these parameters that you will learn more about in 122 and 124. We're just starting with gain bandwidth here. So gain bandwidth, product note 7. And we have some numbers, 15 and 30. I have to scroll back up. Minimum, typical. Okay, so data sheets are written by more than one person in the company with more than one reason. Okay, one is to sell the product. So you want the highest gain bandwidth possible, right? One is by the engineer who doesn't want to have to explain when the part isn't working. So what, and then there's like the purchasing agents, right? Who, and selling agents that if you send somebody a lot of parts, a lot, right? And it doesn't meet specification, can I get my money back? So typical is like, yeah, it's around that, but guaranteed, where did I put it? It's 15. Oh, but LT Spice isn't even saying that, right? So, now, yeah, oh, there's a product note. Okay, product note 7. Let's see. Because usually these things are measured under conditions, all right? Where's product notes? All right. I don't have, I'm trying to find product note 7. But it could mean that there's certain, but here's the thing. Here are the conditions, 25 degrees Celsius, supply, various supplies, right? They're telling you how they tested it, right? So, yeah. Oh, no, no, I don't know where the product notes are. Ah, here we go. 7. Voltage supply, 3 volts. Wait, the power supply is too small. They say you got to have it at plus or minus 15. Okay. So we can just, I can try, right? Mm. It's not really modeling the power supply variation, but um, so yeah, even if they said it was 15, yeah, they're kind of cutting it in half. So maybe, and I've seen this is where LT Spice gives worse results than what they guarantee, and it just could be a back way of like saving people trouble from complaining when things don't work. Okay? So that's why, yeah, you need to know, you read the data sheet, 30 megahertz, you got to make sure you read the minimum, but without LT Spice, it's very hard. But again, you're choosing parts, which ones to buy and all that, right? So anyway, um, the DC gain, open loop gain is up here. Although it's not 90, it's 85. I don't think it was 90 before. I think I was just making that up. Right. So the open loop gain is 85. The gain bandwidth was around 7. And so now you just have to keep below that. Any questions on that? And yeah, you're seeing me doing it live, making a mistake and fixing it, and I'm just talking out loud. Because sometimes that's helpful.
Well, drawing the blue plot by hand, right?
Yeah.
Each break, when it before rolls off, that's where the bowl would be. So even for the face, would it represent that?
Well, the phase should keep going down, right?
Uh-huh.
So this flat region is actually a 0. Oh, I'm telling you, it's wild, okay? But I don't know. I like the part. But we can um, swap out parts. Okay, run it. Okay. Now, the shape isn't looking quite right, maybe to your eyes. But notice the phase here is very flat in this region, right? And really, I'm not, 1 hertz isn't really DC. So the fact that it hasn't leveled out is really just because I'm going too fast. Here we go. Right? So now this part, um, let's call it 130. Its open loop gain is 130. Okay. So that's how you find the open loop gain. Then the gain bandwidth. And again, you're just